we've got one coming up. If you don't want to travel to Australia to see the next solar eclipse, August 21, 2017 is the date you want to put on your calendar. That's the next time it's going to be available here in the United States. It'll be, duration will be somewhere around 1:55 in the afternoon in St. Louis. So that's actually a date I've got circled on my calendar. If you think that's a long ways away, you know, time goes by pretty quickly, as some of you might know. So August 21, 2017 is the date of the next total solar eclipse in the United States. You get to either Salem, Oregon, St. Louis, or South Carolina, Columbia, South Carolina, the totality of the eclipse. So anyway, let's talk about Jupiter. So again, why are we talking about the planets? These are the objects at the next observing session that you're more than likely going to be taking a look at. Jupiter is one of them. And the goal tonight is really to change your perception of the planet Jupiter. We all know it's the largest planet in the solar system. We all know about the banding structure of the eyes and stuff. But my goal tonight is to enhance your understanding of the planet Jupiter. So the next time you look at it in the night sky, either with the naked eye or through a telescope, you don't see it the same way again. Because there's a lot more to these planets when you study them and you dissect them than what meets the eye at first. So that's really the beauty of astronomy. It's like peeling an onion. There's several layers. And as you probe further and you study the depths of these objects in the sky, you really understand, you start to unravel the mysteries of these planets and these objects in the sky, and they become more and more meaningful and more intriguing. So, you know, Jupiter is an object that, I mean, it's very easy to spot. All you do is walk outside tonight and look for the brightest object in the sky other than the moon, and it's Jupiter. So it's easy to find. You know where the Pleiades is, and you know where the constellation Taurus is, you can find Jupiter. So as far as direction, I have no idea what direction it is. I think it's, you know, maybe south that way. So very easy to spot, and it's, you know, it's the largest planet in our solar system. It has more mass than all the other planets put together. So if you take all the mass of the other planets and throw them together, Jupiter has about 2.5 times as much mass as all the other planets put together. It's made of gas. You can see how it compares to Earth. Distance from the sun is about 5.5 astronomical units. So take the distance between the sun and the Earth, multiply by 5.5, and that's about how far away Jupiter is. So these outer planets, again, in the outer solar system are really far away. A day on the planet is about 9.5 hours long. It's called an oblate spheroid, which means it rotates so fast that it kind of squashes at the poles, bulges at the equator. So that's called an oblate spheroid. Same type of phenomenon we see on Saturn. A year is 11.8 Earth days, and it's about 11 Earth. You take 11 Earths, stack them side by side, and that's the diameter of the planet Jupiter. It's mostly hydrogen, and then the rest of it is helium, and then some other trace elements like argon, ammonia, sulfur, and then some other organic compounds. Possibly a dense rocky core, although we don't really know. But it's basically a huge ball of gas, rotating really fast. It's got a lot of moons, a little bit more dense than water, and, you know, 150-pound Earth, a person weighing 150 pounds on Earth would weigh roughly 350 pounds if you could stand on the surface of Jupiter, which you can't because it's a gas giant. But it gives you an idea of the size, the mass, and the density of the planet. So this nice illustration, you can see the Earth here with the moon. If you took 11 Earths, stack them side by side, that's how they would compare to Jupiter. And now you scale this up, and if you took 10 Jupiters and stacked them side by side, this is what it would look like in comparison to the sun. And then, of course, you see how the sun, Jupiter, and that little speck right there is the Earth are in comparison. So the Earth is about 1,000, you know, you could stick about 1,300 Earths inside of Jupiter, and you can stick about 1,000 Jupiters inside of the sun. So the sun is 1,000,000 times larger than the Earth, and Jupiter is about 1,300 times larger than the Earth. So, and then of course you got other stars out there like Aldebaran in the constellation Taurus, and Betelgeuse, and VY Canis Majoris, and some of the other ones that are just absolutely enormous. That would dwarf our sun. That would make our sun look even smaller than the Earth does. So as you study astronomy, you begin to realize just how small we really are. Now, Jupiter. One of the things that makes Jupiter is kind of like our big brother in the schoolyard, all right? Life on Earth, I doubt, would exist very long if you didn't have a planet like Jupiter. All right, Jupiter is like this big, giant mass that gravitationally makes it possible for us to exist without getting pummeled by all kinds of comets and meteors and asteroids. In fact, the surface of Jupiter is hit about 8,000 times more frequently by comets and meteors than the Earth is. And this phenomenon is called the Frisky Effect. What it does is it sweeps through the solar system, sucks these comets and meteoroids in, and either devours them or just flings them out of the solar system, flings them into the sun. It basically sweeps a path out so that it makes it possible for the inner planets like Earth, Mars, Jupiter, Venus, etc. to exist without getting pummeled by these things. So, but of course Jupiter has no value system. It doesn't really care where it flings objects. It just takes them and flings them. So sometimes it flings them out of our path, and then sometimes it throws them into our path. So that's the Frisbee effect. The idea that, it acts like a big filter. In order for life to exist in a solar system like ours, you really need a good Jupiter because it protects us from these objects in the outer solar system, the Oort cloud, the Kuiper belt, etc. They get on a path toward the inner solar system. Jupiter gravitationally keeps them out of our path. And of course, the best example of this is what happened back in 1994 with Shoemaker-Levy 9. You can actually see the scar prints in the lower hemisphere of Jupiter when this comet impacted the surface of Jupiter. So this is the first and only time that we saw a planetary collision in our solar system. And you had a comet that basically was gravitationally broken apart into 20 pieces. And the largest fragment of this comet, when it impacted Jupiter, released a tremendous amount of energy, 6 million megatons of TNT. So to give you an idea of how much energy was released from this fragment that slammed into Jupiter, take every nuclear bomb on Earth, detonate it all at once, and take all that energy and multiply it by 100. And that's how much energy was released when this largest fragment from Shoemaker-Levy 9 hit Jupiter. And a gas plume from that impact rose above the planet about 1,800 miles in space. So, better Jupiter than us. That's why Jupiter protects us. So let's talk about Jupiter's weather pattern. This is where the planet gets really, really fascinating. Jupiter has some of the most exotic weather patterns of any of the planets in the solar system. Because it's larger and has a larger gravitational field, thunder on Jupiter travels 4 times faster than it does on Earth, about 3,000 miles per hour. Rain falls about twice as fast on Jupiter as it does on Earth. You have cumulus cloud convections that pile up much, much higher on Jupiter than they do on Earth. On Earth, they go up about 6 or 7 miles. On Jupiter, they can stack as high as 30 miles. And you really have multiple jet streams. I mean, on Earth, it's much simpler on Earth. We've got the jet stream that goes from west to east, and then you've got the trade winds that go from east to west. Well, on Jupiter, you have multiple jet streams going back and forth. So take what's happening on Earth and put it on steroids, and scale it up. And that's essentially what the weather pattern is like on Jupiter. Now, we're all familiar with the banding structure. We see this when we look at either pictures of Jupiter or we look at it through a telescope. And scientists have broken this down. So the darker bands are what are called belts. And then the lighter bands are what are called zones. All right? And you can see here kind of a diagram. You've got the zones on the right side, you've got the belts on the left side. So the belts are the darker regions, and they're really areas of descending air mass. The source of the color, in terms of the dark pigmentation, isn't exactly known. The light bands are called zones, and those are really areas of upwellings of air masses within the planet. And they're cooler in temperature than belts tend to be. And their lighter color is due primarily to clouds of ammonia that form ice crystals of ammonia in the upper atmosphere that reflect more light. So really, I don't want to get into too many details of the weather patterns on Jupiter. That could be a separate presentation in and of itself. But scientists have divided these bands, the darker bands and the lighter bands, into different zones and different structures. And you have airflows going back and forth between the two. So, and there's a lot of dynamics going on within Jupiter's atmosphere. You see storms forming, merging, dying. You see just a lot of movement. The origins and the exact nature of the weather patterns on Jupiter is still not completely known. It's an area that's being studied. But the two main models that are out there are what's called the shallow model and called the deep model. And the shallow model basically postulates that the surface weather on Jupiter is basically occurring on the surface and there's a stable core or a stable interior. Where the deep model is a theory that there's a lot going on, basically that what's happening on the surface of Jupiter weather-wise is a manifestation of what's going on deep within the planet. So you basically have deep circulation over multiple layers within the planet, and it's being circulated up toward the surface of the planet. So I tend to, based on my readings, my research of the planet, tend to more or less fall in line with the deep model, but really to explain the behavior of the weather patterns is probably a combination of the two. But again, I just want to mention it here. North tropical zone, or temperate zone, north temperate zone, tropical zone. This is the equatorial zone. It's calmer here than it is up in these areas right here. And then of course you've got the north temperate band, belt, north temperate belt, north equatorial belt. So that's what this nomenclature here is. And you can actually see an illustration of the weather patterns on Jupiter here. So you can see here the equatorial zone, lighter color, the north equatorial band, the south equatorial band, the red spot here moving in a counterclockwise or anticyclonic motion going from left to right. You see different ovals up here, storms that are forming and dying off. And then you see some of these bluish gray patterns here on the region between this band here and this equatorial zone here, which is more weather patterns that are forming. And there's just a lot of dynamics going on within the Jupiter atmosphere. Yes?
I think it's kind of neat the way those black spots, the satellite shadows show up in there too.
You see some of the satellites going past. This is actually a 14-frame animation. So what you're seeing here is over a period of 10 Earth days or 24 Jovian days, sped up about 600,000 times. And yeah, you can actually see the shadow of some of the moons going by, Europa, Io, Callisto, some of the bigger moons of Jupiter. So,
I think which bands are going up and down because of how they see things in the motion of the.
I'm sorry? Which bands are going up?
You said that the lighter color is coming up and the darker color is going down.
Right. Updwellings and downdwellings of weather patterns.
Is that because of what shows up in the motion?
No.
Or do they use a infrared?
Part of it is the composition of what's in each belt and what's in each zone.
So they can see things disappearing down.
Yeah.
And emerging up. Okay.
Some of it's understood, some of it's not understood. Like the darker regions, why are they dark as opposed to light? That's not completely understood. As far as, the differences between the bands in terms of motion, in terms of composition, I don't completely understand all of that. I'm not really sure I mean, it's still an area that's still being studied. There is a lot of research out there on it. There's a lot of information out there on it. Most of it, to be honest with you, is kind of beyond my level because I'm not a planetary scientist. I'm not a meteorologist. What I'm doing here is just kind of giving you an overview so we see how it's laid out, how it's structured, and kind of how it moves. But to be honest with you, this is one of the great mysteries of the planet. It's an area that's still being studied. It's an area that's still being researched. And it's an area that still raises a lot of questions among scientists. Because we should understand this. Because we see the same type of phenomenon on Earth. And yet on Jupiter, it's just more complex. It's more complex, it's more dynamic, and it's more mysterious. So you have scientists who are literally devoting their entire careers to studying this stuff. And as technology improves, and one of the things you mentioned is infrared imaging of the planet. And we'll talk more about that later in this presentation. But Jupiter has a fascinating heat signature because of how much heat it radiates, which is why I tend to follow the deep model hypothesis in terms of explaining the weather patterns. I think there's more going on within the interior of Jupiter, which is what we see on the surface in terms of its weather patterns because of how much heat is being radiated from the planet. So I know that's a long answer to your question, but part of it is some things we do know, some things we don't know, some things we're still trying to figure out. That's the best way I know to answer. You got a question?
How deep into into Jupiter's atmosphere have they been able to go with the infrared? All the way up to the surface, or have they gotten that far?
How deep can
they see? Can they see image?
I mean, when you image Jupiter in the infrared, you're basically seeing, different the heat signature that's on the surface. There's different cloud layers. You can't. I mean, as far as how deep into the planet, I don't know. But you can take a snapshot of Jupiter in the infrared, and you can see the dark and the light colors, and see, the darker areas being the cooler regions, and the lighter areas being the warmer regions. But as far as how deep in, to be honest, I don't know. Yes?
The infrared, the thermal infrared, typically 8 to 14 microns or so. You don't really see all that much deeper, but what you do see is the thermal emissions rather than just the reflected light. That's the significant thing. And you're going to be mentioning about that in a moment. But the main thing is you're seeing down into the atmosphere to a point where the atmosphere is what they call optically dense, which means that you get to a point where the scattering is so much that it's just not, you don't see penetration any deeper. It's not really different between optical and the thermal infrared. So the depth is not very different.
Right. What satellite is it? Is it WISE that does the infrared imaging?
This is same kind of wavelength. But the main thing is that, of course, WISE is looking, things out in space, whereas if you're looking at Jupiter, you're looking into an atmosphere. And it's sort of like, think of Jupiter actually as something like a small star. It's even smaller than a red dwarf star, and it's cool enough that you start getting chemistry and things like that. But the rapid rotation introduces very strong Coriolis effects, which result in bands and things like that. So, but you'll see if when you get into studying red dwarf stars and such, there are a lot of red dwarfs that rotate very rapidly, and you see the same kind of things, the same complications in the atmospheres and such.
And brown dwarfs too. I mean, they're about 40 to 75 times larger than the planet Jupiter in terms of mass. But yeah, you see a lot of the same complex weather patterns and really, really violent winds on some of those worlds too, especially brown dwarfs.
And if you get into the magnetic fields and interactions with the moons and such, the same kind of things.
Yeah, interesting. So that would be a fascinating and probably, quite frankly, a boring presentation. Just the weather patterns on Jupiter, just dissecting it and going through, because there's so much information out there. And it would probably be, I could do it, but I probably wouldn't be the most qualified to do that. But a planetary scientist or someone who studies this stuff full time, because it is interesting. It is fascinating. Because these bands, this is a simplified model of how it's laid out, but the dynamics of it, in terms of how it's interacting, and then you've got certain bands that splice and reconnect. Yeah, there's a lot going on. So, but for the purposes of this presentation, since we're kind of doing a survey, I just want to mention it. So, anyway. Now, let's talk about the red spot, because this is probably the most well-known feature on the planet. And we all know it's a giant storm. It's about 2 to 3 times the size of Earth. It's anticyclonic, which means it rotates counterclockwise. Now, for the southern hemisphere storm, that's counterintuitive, because on Earth, a southern hemisphere storm would actually rotate clockwise. So it's not a low pressure system, it's a high pressure system, which is very interesting. It's been around, we know, for the better part of 400 years. It was first observed in the 1600s. You have wind speeds up to 350 miles per hour in the storm. You know, compare that to the fastest wind speeds on Earth, 231 miles per hour. And what's interesting is this storm is actually, much higher in terms of its distance than other clouds within the planet. And cloud tops tend to be cooler. I don't have an infrared image of this, but it'd be interesting to look at, comparing the red spot in the infrared to other cloud tops within the planet. And the most violent storms are actually on the outer edge of the Great Red Spot. The inner part of the storm, of the spot, tends to be calmer. It's not like a hurricane in that it has a well-defined eye. It doesn't have that. But the wind speeds in the center are much calmer and much more violent on the outside of the storm. And of course, it's the largest storm in the solar system. Now, the source of the Great Red Spot is still a mystery. It's not, on Earth we have hurricanes that form over a body of water. And then, depending on the strength and the intensity of the storm, it's more well-defined. When it slams into land, it dies off. So on Earth, these storms tend to last at most 2 weeks. But this Great Red Spot has been around for hundreds of years. One possible theory for the source of the storm is what's called an atmospheric volcano, where you have warmer heat or warmer gases rising from heat deep within the planet that are trying to escape, and in so doing they form this vortex, rapidly spinning vortex. And it's kind of like a large tornado or a large vortex within the planet that causes the storm and has been sustaining it for a long period of time. But to be honest, it's still kind of a mystery, and there's still several unanswered questions regarding the storm. Why is it so well formed? Why does it stay around for so long? And there's no ocean over which it forms, so what is powering it and what is sustaining it? But likely it is due to internal heat within the planet trying to escape, forming a vortex. Now, what's interesting is the Great Red Spot is not the only large storm within the planet. There's other things going on here. And one of the things that happened recently is the formation of a cousin of the Great Red Spot called Red Junior. So if you look at this image right here, you see 3 white spots, which are kind of cousin storms of the Great Red Spot, smaller. And these were first discovered back in the 1930s, and they actually merged to form a larger white spot, which eventually changed color later on to form a cousin of the Great Red Spot called Red Junior. And you can actually see the dynamics of this happening here. So these 3 spots were first observed back in 1939, FA, DE, and BC in the south temperate zone. And these 2 right here, this is 1997. A year later, in 1998, they merged to form this spot right here, BE. And then, of course, later on, these 2 right here got close together, and they merged to form BA, otherwise known as oval BA. All right? So from 1997 to 2000, these 3 spots right here merged into one spot right here called oval BA. And then in 2005, mysteriously, it turned from white to red. So it changed color. And that's why it's called Red Junior. Tony Phillips of NASA actually named it Red Junior. Now, the reason why it turned red is not completely known, But one of the theories is that, again, gases deep within the planet, due to powerful winds, were somehow churned up, brought to the surface, and when they reached the surface of Jupiter, interacted with sunlight, and when they were exposed to sunlight, they turned red. So that's one of the outstanding theories there for why storms turn from white to red on the surface of Jupiter.
Can they use spectroscopy to determine what gases they are?
They can, and then they can take those gases and see how they interact with sunlight. But it's still not completely known what those gases are, and the dynamics of what's happening internally within Jupiter are still not completely known. So you can see an image here, great red spot, and red junior, oval BA. And I like this image too, from 2008. You can actually see, again, another storm, a smaller cousin yet, 3 of them. Great red spot, oval BA, red junior. And then you've got mini red junior, or baby red junior. And then this guy right here gets too close to this guy. And then this guy right here eats this guy. So you still have red junior and you've got big red spot. So don't mess with the big red. So anyway. Okay. So, that's the great red spot. Lots going on. Now, I love this exercise. This is where Jupiter gets interesting. We're going to take a journey, a hypothetical journey, into the core of the planet Jupiter. All right? Now, I'm sure you guys have seen this before, but let's go ahead and do this again. So let's just say sometime in the distance, there's no way we could ever develop a spacecraft that could actually do this. So let's just say a few hundred years into the future, Star Trek Enterprise W is invented, and it can withstand the extreme pressures and temperatures internal to a core like Jupiter. And we're actually going to fire off this spacecraft. We're going to go inside the planet Jupiter, inside the core, and find out what we see. So we start out at the upper cloud levels, we plunge in, and we would see a scene similar to this, kind of a bright orangish reddish tint. We're flying through clouds, and there's a lot of different compounds. We see basically the sunlight interacting with compounds of ammonia, carbon, methane, phosphorus, and sulfur, primarily sulfur. A lot of storms, a lot of lightning, a lot of turbulence, and not a very pleasant smell. Because you have sulfur, you're going to have the smell of rotten eggs as you're descending through the cloud tops of Jupiter. So that's how the trip starts off. As you plunge deeper within the planet, the pressure increases. It's similar to what happens on Earth when you have an airline jet that's high up in the atmosphere and it lands. You get that ear-popping sensation. Multiply that by a very large factor and you have the same type of thing going on the planet Jupiter. You're descending through different layers of gas or different layers of clouds as you plunge into the atmosphere of Jupiter. So the pressure and the densities become larger, the gas gets more and more compressed, the pressure increases, and what happens is the properties of this gas change because of the pressure. You eventually reach a point where the gas, which is hydrogen, stops acting like a gas because of the pressure. And that's where it gets interesting. Because after you descend about 13,000 miles into the core of Jupiter, what happens is the pressure becomes so great that the atoms and the molecules that make up hydrogen no longer behave like a gas. They actually behave like a liquid because they're being squashed together. So you actually descend onto the surface of liquid hydrogen, which is similar to, that basically is the surface of Jupiter. Now, it's not like when you land on Earth, like on an ocean where you have a liquid of water and then air. An extreme boundary or a very clearly defined boundary. On Jupiter, if you plunge through these different layers, it's like the air becomes thicker and thicker and thicker, and you're almost descending through kind of a dense soup or a dense steam that becomes more and more like a liquid as you penetrate these different layers, until finally it basically is a liquid layer or a surface of liquid hydrogen layer. It becomes like a hot liquid layer. So that is essentially the surface of Jupiter. Now, if you plunge down even further, it gets even more interesting. because there's another layer below this layer of liquid hydrogen. And that's called liquid metallic hydrogen. If you plunge down even further, the pressure becomes so great that the hydrogen, the liquid hydrogen layer, acts like a liquid metallic hydrogen surface. So the pressures increase, the temperatures increase, and the electrons that are bound to their parent atoms strip away, and they no longer are bound to just one individual atom. It's like a sea of electrons, which is what you get inside of a metal. On this surface, it's bright, it's blue, it's brighter than the surface of the sun. The temperatures inside the core of Jupiter are hotter than what you would see inside the surface of the sun. And this liquid metallic hydrogen layer is a very good conductor of heat and electricity. In fact, the most abundant liquid, or the most abundant metal in the solar system, the most abundant liquid in the solar system is liquid hydrogen. The most abundant metal in the solar system is liquid metallic hydrogen inside the core of these gas giants. So this is a kind of a fascinating property internal to Jupiter. The pressure is extremely great. If you've ever had someone step on your toe with a stiletto heel, not a good time. Now imagine that person weighs as much as an elephant. Now imagine you have 1,000 elephants standing on top of a stiletto heel, standing on your toe. And that would be the simulated pressure within the core of Jupiter. It's pressure over 100 million times greater than what you would get on Earth. So that's what's going on inside of Jupiter. And if you were somehow flying in a spaceship around this liquid metallic hydrogen layer, you would see a discharge of electricity. And it would be a very violent and volatile environment. So the liquid metallic hydrogen interior of Jupiter has properties unlike anything we have ever seen on Earth. It's also the source of Jupiter's magnetic field. The closest thing on Earth to liquid metallic hydrogen would be molten liquid steel. Have you ever seen at a steel plant where they pour it out in the cauldron, see the bright steel falling? It has electrical properties. That's the closest thing to liquid metallic hydrogen on Earth. Yes?
Question, this is kind of off this a little bit, but still kind of on the same area. Shoemaker-Levy, I'm assuming that the depth of the surface and everything, when you're going in with Shoemaker-Levy, and I would think that Shoemaker-Levy would kind of indicate that the surface would actually have to be a lot closer to the cloud base. Otherwise, I wouldn't think you would see the plumes from Shoemaker-Levy if it was actually 130 miles from the upper surface. And Shoemaker-Levy, the actual objects only being like about 2 miles wide. What do they think the reason that you would see the plumes from Shoemaker-Levy if the distance into the surface was that depth?
Well, okay, so when a comet gets swallowed up by Jupiter, it's basically descending through different layers.
Right. But I would assume that it would cut through the cloud base until it got down to the surface. And the closer the surface is to the upper cloud base, you would see the plumes coming up. But the deeper, it seems like the cloud base would cover plumes of something 2 miles wide, if you understand what I'm saying.
The best way I know how to answer that question is it's similar to what happens on Earth when a meteoroid burns up in our atmosphere. It's on a much larger scale. When it burns up, it's the friction of the atmosphere as it's falling in is what causes it to burn up. In the case of what happened on Jupiter, you have this large object that's plunging through these layers at a very, very high speed, and eventually at some point in time there's going to be an explosion. When there's an explosion, there's a rebound. And that rebound is going to shoot gases up out of the surface of Jupiter. And it's that explosion and that tremendous release of energy is what caused the 1,800-mile high gas plume to explode. So it's really more of a physics scenario than chemistry.
It never hit the surface.
No. Jupiter doesn't have a surface.
Never hit
But it never got to the,
Yeah.
no. That's over 13,000 miles into the planet's core. I mean, the purpose of this exercise here is to show you how the properties of the hydrogen gas change under extreme pressure.
I think that's what he was thinking.
That I got to this point? Yeah, no. Yeah, I mean, yeah, the meteor, the fragment of Shoemaker-Levy would have exploded long before it got to this layer here. And, you know, there's no way to directly prove that this exists. We infer this. This is one way that science is used as a tool to infer what is, based on doing, basically by applying the scientific method, collecting the data, doing observations, testing a hypothesis. We know that Jupiter has a magnetic field. We'll talk about that later. What's causing the magnetic field of Jupiter to exist? Because the source of Earth's magnetic field is the molten core, the molten iron core within our planet. So we know that Jupiter doesn't have a molten iron core, so what is the source of Jupiter's magnetic field? Well, by using, again, the scientific method, and by analyzing what would happen to hydrogen under conditions of extreme pressure, we can infer that this ocean of liquid metallic hydrogen exists, and based on its properties as a metal, we know that that has to be the source of Jupiter's magnetic field. So, you know, science is part observation, data collecting, experiments, and all the nerdy stuff that we do. But there's another side of science that, in my opinion, is just as fascinating and even more fascinating, and that is when you can use your imagination and perform what are called thought experiments. That's one of the things that Einstein was so good at doing. You know, Einstein, for all his genius and all his brilliance, Copernicus too, these guys, the real genius of Einstein and Copernicus is that they were able to perform thought experiments. They could extract things. Copernicus is dying. He doesn't have a telescope. He doesn't have any type of instrumentation. And for the last 13, 14, 1,500 years, everybody knows that the Earth is the center of the universe. And all of a sudden Copernicus comes along and says, you know what, I don't think that's right. I think the sun is the center of the universe. And it was so controversial at that time to think that way that you wouldn't even dare to publish it because your life was at stake. And yet he had the guts to publish it on his deathbed, and he turned out to be correct. If it hadn't been for Copernicus, Kepler wouldn't have come along, Galileo wouldn't have come along, Newton wouldn't have come along. So, and again, it was because of the imagination. Einstein did the same thing. I'm on a train. I'm looking back at the clock tower in Switzerland. What if I was traveling at the speed of light? What would I see? The light from the clock tower wouldn't catch up to me because I'd be going at the speed of light. And from that, he deduces the theory of special relativity. And then he deduces the theory of general relativity. And then the next solar eclipse comes along, and they prove that it was correct. And he not only proved that it was correct, but he actually calculated the angle that the light from the star behind the sun would have been bent as it passed by the sun. That's another reason why solar eclipses are so fascinating, because they were used as a tool to prove Einstein's general theory of relativity. Einstein performed a thought experiment. He didn't perform a real experiment, he performed a thought experiment. We can do the same thing here by analyzing Jupiter's core. We can take a hypothetical journey in our minds into the core of Jupiter and imagine what it might look like at the surface of this liquid metallic hydrogen layer. Bright blue, brighter than the surface of the sun, electrons behaving like a metal, like they would in a metal, and basically the properties of a liquid and a metal within the surface or within the core of the planet. So that's the purpose of this exercise here. Imagination, thought experiments. Sometimes you got to think like a hardcore scientist. Sometimes you think like a child. Put the two together and you've got something really, really cool. Really, really fascinating in science and astronomy. Okay. Now, finishing this exercise, if you were somehow able to take a cup full of this liquid metallic hydrogen and instantly transport it to Earth, it would be extremely explosive. Far more explosive than TNT. In fact, it would be analogous to a hydrogen bomb going off because it's under extreme pressure. So the properties of hydrogen in the core of Jupiter are very, very different than what our intuition tells us that hydrogen would behave like. All right, so Jupiter radiates a lot more heat than it actually takes in from the sun. In fact, it radiates about twice as much heat as it does than it receives from the sun. The temperature inside the core of Jupiter is about 40,000 degrees Fahrenheit, hotter than the surface of the sun. It contains a vast ocean of liquid metallic hydrogen, which is, of course, the source of Jupiter's magnetic field, which we'll talk about a little bit later. Well, let's talk about the moons of Jupiter. Again, like Saturn, the moons are kind of where the action is. And the four main moons, Europa, Io, Ganymede, and Callisto, were first discovered by Galileo. And he actually used a telescope to observe them back in 1609. And for years, these were the four main moons that were known. It wasn't until the end of the 19th century that the fifth moon was discovered. And since then, we've discovered dozens of moons, all right? Between 1999 and 2003, there were 32 additional moons that were discovered. A few years ago, there were an additional 20 moons. So Jupiter has a lot of moons. Depending on who's counting, it could be anywhere from 67 to several hundred. We're just going to focus on the four main ones, which are the Jovian moons: Io, Europa, Ganymede, and Callisto. And I just want to talk about a couple of them today, because it's fascinating. So let's talk about Europa for a minute. Now, Europa is a moon that kind of has a special place in my heart. When I was working on my master's thesis in college, the team that I was on was tasked with designing what are called primitive analog circuits to go on a space exploration probe to the moon Europa. It was a project for the Jet Propulsion Labs in Pasadena, California. Most of our electronics are made of a VLSI technology called bulk CMOS. I'll spare you the details, but your iPhone, your computer, the electronic circuitry in your toaster, in your car, everything uses bulk CMOS, complementary metal oxide semiconductor. It's great on Earth. It's not ideal for the environment of outer space, where you have extreme temperatures and radiation from the sun. So the research project that I did for my master's thesis looked at designing transistors with what's called SOI technology, silicon on insulator, which doesn't use wells, and it's not prone to what's called latch-up. So forget all those details. The bottom line is, 10, 15 years ago when I was working on my master's thesis, the group that we were working for was based out of California in Jet Propulsion Laboratories, designing a space exploration probe to go to Europa. Why Europa? Because Europa has a lot of water on it. In fact, it's basically a smooth surface that contains it's covered with ice, 6 to 19 miles thick, and it contains a vast ocean of liquid water. More water than what's on Earth's oceans. And anytime you have water, there's a lot of curiosity because you could possibly have life. So this is one of the worlds that NASA is focusing on for future exploration, because there could be life on Europa. And you can see the surface features here. It's like a cracked egg. As Europa orbits Jupiter, the tidal forces stretch and pull at the moon, and you see cracking that's going on. And the thinking is, it's basically a solid shell of ice floating on top of the liquid ocean. And if we could somehow go ice fishing on Europa and drill down and get inside that ocean and analyze what's underneath, maybe we'll find primitive forms of life. And there's actually a project going on right now by a physicist and an engineer named Bill Stone, and he's designed a probe, and he's testing it right now, called DEPX, Deep Phreatic Thermal Explorer. This is an autonomous robotic system that's designed to explore the oceans, first on Earth, and then eventually travel to Europa. So when we send a probe out in space, like to Mars, every movement of that probe on the surface of Mars has to be given by command here on Earth. This thing is different. This is supposed to be autonomous. basically you have a system where you plunge it into the ocean and it can actually navigate itself around and find out, I mean, basically it can propel around, look, find certain areas that it wants to explore, take samples, analyze them, and then give feedback back to Earth. So it's an autonomous robotic explorer, or a hydrobot. And this thing's been under construction for several years now. The plan is to launch a mission to Europa sometime in the next decade. You know, preliminary was 2016, get to Europa around 2018, and then hopefully by, you know, the end of the decade, we'll know one way or another whether there's actually primitive life forms on Europa. And this is kind of how it would work. You would have a parent vehicle here, which would travel to Europa, launch a probe that would land on the surface of Europa. And this would contain the physical landing system, the rocket systems, power, data relay, everything. Once you're on Europa, you would have a drill that would basically drill into the ice cap of Europa, all the way down. And when you get to a certain stage, you launch what's called a fiber optic cable that contains the communications and navigation system, as well as a power pack. And then you have what's called basically a torpedo-shaped submarine that explores the oceans of Europa and looks for life. It has an onboard microscope. It can collect samples. It can analyze the samples up to 5 microns in width, and then it can relay the information back, seeing if it has anything interesting to look at. It's being tested right now on Earth. It's been tested in the oceans off the coast of New Mexico, or of Mexico. And the next stage in the development is actually to try this out in extreme frozen areas of Earth, such as Antarctica or Alaska, and then eventually launch it to Europa. So, bottom line is, Europa is a world of interest, has been for a while, and engineering is in the works to send an autonomous probe to Europa to explore the oceans.
How thick is the ice?
I've heard anywhere from 6 to 60 miles. Based on this project, they're assuming it's somewhere between 6 and 10 miles, because the maximum that it can drill down is about 10 kilometers. So, yeah, the range is pretty wide here as far as the...
Can they tell with radar mapping?
Possibly. It's not as thick as they originally thought. Based on what I've read and researched, initially, what I read and researched, 60 miles of ice, 60 miles of ocean. What I'm reading now is that's been revised to somewhere between 6 and 10 miles of ice and then 60 miles of ocean underneath. So the ice cap isn't as thick as initially thought. The reason is because you see a lot more cracking. So the thinking is, if there's more cracking, maybe there are areas where the ice is cracking under tidal forces due to gravity, and some of this water is actually, you know, coming up through the cracks and then refreezing. So maybe it's not as thick as they initially thought, making a project like this more realistic. Obviously, drilling through 60 miles of ice is not going to happen.
Then they could drill through a crack.
Maybe. So, and again, on the bottom of the ocean, on Earth, we have what are called hydrothermal vents, areas where heat is coming up through the ocean floor. We have, you know, where life can exist and be sustained, possibly tube worms. I don't think we'll find tube worms or anything complex in Europa's oceans, but it's all about the bacteria and the, you know, the primitive life forms. We can find bacteria or single-cell organisms on some world other than Earth, and that means that life is very common in the universe, and there is no God, and we all evolved, and we live in peace and harmony and everything else. So that's the idea. I'll believe it when I see it. So anyway, Europa. Now let's talk about Io. Io is another fascinating world. It's the 4th largest moon in our solar system. It's about the same size as Earth's moon. It's the closest of the Jovian moons to the planet Jupiter. And it's constantly being tugged and pulled, both by the gravity of Jupiter and then also by the gravity of the other Jovian moons like Europa and Ganymede. In fact, it's in an orbital resonance with Europa and Ganymede. So Io is constantly being pulled and stretched. It's like playing with a lump of clay or a lump of Play-Doh. As you knead it, it's constantly being stretched and it heats. Well, that's what's happening on Io. It has over 100 active volcanoes that's just spewing lava out. And it's literally bursting at the seams. New Horizons, spacecraft bound eventually for Pluto, took several images of Io as it flew by and saw dust plumes emanating from the surface of Io, some as much as 200 miles high. And Io has lava flows, some of them 300 miles in length. Some of the volcanoes on Io are about the same size as the state of California. Just an immense amount of lava is being erupted constantly from the surface of Io. About a ton of material is spewed into space every single second from the moon of Io. And this volcanic ejecta gets swept up into Jupiter's magnetosphere and forms what's called a plasma torus around Io. It makes it an environment of an extremely hostile environment. High radiation, high radioactivity, very, very toxic. A human traveler to Io or to Jupiter, unprotected, would only survive for a matter of minutes before they'd be killed by the radiation. So, the fascinating thing about Io is, as these charged particles, as this material is being ejected into space and swept up by the magnetosphere of Jupiter, it creates what's called a nebula, or a gas cloud, around the planet Jupiter that's extremely large. In fact, it's about 500 times bigger than the planet Jupiter itself. All right? In fact, it's the largest stationary object in the solar system. And again, you can see kind of the effect of this. What happens is this material is ejected from the surface of Io, it gets swept into the magnetosphere, and then you have the solar wind, charged particles from the sun, electrons within the magnetosphere of Jupiter that are ionizing this material, stripping it of its electrons and exciting them, right? Forms this plasma torus, this nebula, this cloud of material around the planet Jupiter. Enormous. And this was actually photographed back in 1990 by Michael Mendello and his team at the University of Boston. They used a digital camera at that time attached to a telescope, and they photographed a dust cloud. This is what it looked like. And one of the elements that they used to photograph this cloud was sodium. It's only about 5% of the material that's ejected into the cloud. But sodium has kind of an orangish, yellowish glow, kind of like what you see in streetlights. And you can see this. So by using digital cameras and taking multiple images and superimposing them on each other, you can actually photograph this dust cloud, or this nebula of Jupiter. And in fact, it's so large that if it was visible from Earth, right now, if you could see the cloud from Earth with the naked eye, it would be the size of 12 full moons in the night sky. So imagine walking out tonight and looking at Jupiter and see 12 full moons, 4 wide by 3 deep, basically a grid of 4 by 3 full moons. And that's what this nebula, or this gas cloud of Jupiter, would look like if it were visible from Earth with the naked eye. Enormous. The largest stationary object in the solar system, by far. So that's what Io is doing. It's creating an extremely hostile environment of radiation and radioactivity, as well as a gas cloud around the planet Jupiter that's enormous.
You said stationary, is it not in orbit with Jupiter around?
Well, it moves with Jupiter, yeah. It does, I mean, the gravity of Jupiter is moving it.
Okay.
So, yeah, it moves with Jupiter. Yeah, stationary. I guess you got to be careful how you define that term. But yes, it is moving with Jupiter. All right, so let's talk about Jupiter's magnetosphere. The largest entity in the solar system is not the sun. I mean, initially I thought it was the sun. When you do research, you think it's the sun. Jupiter's magnetosphere is larger. It's the largest entity in the solar system. Larger than the sun, It's a bubble about 450 miles long. It's got a windsock type pattern, all right? So magnetic field, this is the front. You have similar type of thing on Earth, where you have a long windsock type pattern in the back. This right here extends out to the orbit of Saturn. Enormous. It has an extremely powerful radiation environment. It generates up to 10 million watts or amps of current that are flowing through this magnetic field. If you could see the magnetosphere from Earth, it would appear 5 times larger than a full moon. And what happens is solar wind from the sun, charged particles, are being captured by the magnetosphere of Jupiter and causing these large currents to flow. So you have an environment of extreme radiation, and you have an environment of extremely high electrical currents that are flowing. So it's enormous, and it's enormously powerful. And it produces auroras on Jupiter, much like what we see on Earth. In fact, the auroras on Jupiter are as large as 1,200 miles in size, and they're 1,000 times more powerful than the northern and southern lights on Earth. If it were possible to stand underneath them on Jupiter, they would fill up the entire sky, and they would be bright and brilliant and moving very, very fast. The fascinating thing about Jupiter's magnetosphere is you can actually hear it occasionally. If you're driving down a desert road in the middle of nowhere late at night, tune in your AM channel somewhere in the mid to upper band, and you may be able to hear the magnetosphere of Jupiter. It's a creepy, eerie sound. You can hear roars like lion roars. You can hear sometimes hissing. You can hear whining, moaning, kind of the sound of waves crashing on the ocean. It comes in short and long sputters. But Jupiter's magnetosphere is constantly pulsating and sending out signals that can be detected occasionally by the AM band here on Earth.
Have you heard it?
I have not. I have not actually heard it myself. So it's not something that you could probably hear here in Mississippi.
Have you heard it, Roy?
Oh, if I might suggest, I was reading an article recently that the activity, you can principally hear it in what's called the decametric band, sort of like around 30 megahertz or thereabouts, and it's related to the position of Io in its orbit. I forget all the details, but you can Google it pretty easily. Just Google Jupiter radio emissions Io, and an article that you might find indicates that, as I recall, when Io is on one side of the planet, it's the whole the torus tube stuff. You'll hear more activity in that particular orientation, but I can't remember all the details. But it is available on the internet if you do a Google search. But yeah, if you have like a shortwave radio late at night when the ionosphere is relatively quiet and you're not getting propagation from very distant stations, the ionosphere will become relatively transparent to these decametric radiations, 30 megahertz or thereabouts. And yeah, if Jupiter, what you might want to do is listen before Jupiter rises, and then notice any increase in His or S meter reading as it rises. But yeah, the main thing was the position of Io with respect to Jupiter indicates when the best time is. That's all I can suggest. Google search would help find that article.
Why is the position of Io important?
Oh, it's the way the Io torus, the ion torus, is lined up around Jupiter. A lot of the radiation is cyclotron radiation, things like that. Anytime you get electrons spiraling in a magnetic field, you get radio emissions. I forget all the details, but the main thing that stuck in my mind is that if you're wanting to listen to Jupiter, you wait until, Sky and Telescope has these tables indicating the position of Io with respect to Jupiter at different times. And you wait for a night when it's going to be Io will be on the particular side of Jupiter that's important. And then you have a receiver that's, a shortwave receiver that it will pick up 25, 30 megahertz or so. And late at night is best, although you could try during the daytime, but usually during the daytime you get all sorts of noise from the atmosphere and distant radio stations and things like that.
Yeah, night is better, later at night.
Yeah, late at night when the ionosphere, the propagation is very good for lower frequency, but the high frequencies, you normally get long distance propagation during the daytime, and at nighttime the refraction of the F layer is such that it doesn't refract all the way back down to the Earth, and the atmosphere is essentially sort of transparent to these really high frequency wavelengths.
Yep. Did they say what band is best to listen to it in?
If you have amateur radio gear, 10 meters, or if you have just a shortwave radio, something in the 25 to 30 megahertz range. Like say decametric, 10 meters wavelength. So about 30 megahertz or thereabouts.
About 9 meter, yeah.
I'm sorry?
About 9 meter, you're saying. You're saying 34, that's going to get you around 9 meters, yeah.
Yeah. So, like I say, do a Google search to see if you can find that article. That would be very helpful. I can't remember all the details though.
So there it is. So wrapping up, again, the moons in our solar system are where the action is. Io, Europa, possible source of light. Io, very active volcanically. And, there's lots of moons. We just touched the surface on this one. The core of Jupiter contains the most abundant element in the universe, source of the magnetosphere, which is the largest entity in our solar system. And the biggest thing is the planets don't give up their secrets very easily. There's a lot of layers. When you study these things, there's a lot below the surface. Now the Jupiter magnetosphere, the dust cloud, the moons, and of course the weather patterns. There's a lot going on the planet Jupiter. A lot of dynamics, a lot of intrigue. So that's why we study the planets. Next time we look at it through the next observing session, hopefully you'll see it a little bit differently. But that's it. That's my talk.
I would say another thing is it's nice that our solar system has all this variety, we'll say. It's got a little bit of this, like Saturn's got the rings, and
Yeah.
each one seems to have, Venus has got things. And
Venus has the extreme environment, or extreme pressures, 892 degrees Celsius on the surface, sulfuric acid rain. Saturn has Titan, liquid methane
so all this,
cryovolcanism on Enceladus, as well as the ring structures, and now Jupiter.
yeah.
Neptune, 1,400 mile an hour winds.
Ooh.
So, yeah, a lot of variety in the solar system.
And Pluto got.
So there you go, guys. Appreciate it.
Well, there's this one, hopefully, we'll see you next month.